Well, good afternoon, everybody, and thank you very much for taking time out during your lunch break during this lockdown for a nice little distraction and also hopefully a great educational experience. We're very fortunate to have John McClune from Wolfram Research. John is a Director of Technical Services, Communications and Strategy at Wolfram. And he's going to be talking to us this afternoon about big problems with big data, managing risks in AI. I think this is an incredibly important and very topical subject, and hopefully we'll get quite intrigued by the concepts and ideas that John's going to be revealing to us today. Anyway, I'd also like to thank at this stage Corriculo Limited, who is our fantastic sponsor for the Data Science Oxford meetup. They've supported us over the last several years, and also during this lockdown period, have been very kind to provide us with a Zoom business account to allow all of us to share these experiences. So before we kick off, I'd just like to go through a few housekeeping rules, please. This session is being recorded, so I know some of you need to leave a little bit early during the lunch break, so you'll be able to catch up on it later on. We would ask you please to remain muted for the duration of the presentation. And if you do have any questions, then please do feel free to ask those questions in the chat. We will be monitoring that. And hopefully John will be able to get back to answering some of those questions about his presentation at the end of the session. I would also encourage, just to promote the kind of community feel of this meetup, for you to turn on your video if you can. It'd be great to be able to see your reactions to the conversation and maybe give John the important cues that he needs to make it, an interesting conversation as well. Can we go on to the next slide, please? Thanks. What we plan to do in the next hour is to kick off with a brief up to 10 minutes conversation, a word from our sponsors Corriculo on the current state of the data science jobs market. I thought that might be a very interesting topic for our community to try and understand, particularly during this lockdown period. We know quite a number of people are struggling with jobs, and I thought they could give us a great insight into what's actually happening in this space. What are the opportunities out there? What is the temperature in the marketplace for these types of jobs? And then we'll transition into John's presentation for about 50 minutes, and then we'll close that with Q&A. One of the things I would like to emphasize, please, if we want to keep this meetup and this community healthy, your feedback is really vital. And as organizers, we will try and take all of that feedback into account to bring, great talks like John's going to be presenting from people who have a tremendous amount of experience in the industry, and try and keep this meetup focused on things that are more pragmatic and applied. So please do leave comments and suggestions for what you want to learn going forward in the community chat or the discussion pages on the meetup. Great. Next slide, please. I will be posting these links down here for upcoming Wolfram events in the meetup, so I won't dwell on this any further. And so let's invite Dan Hicks to come and talk to us about the state of the data science job market. Thanks.
Perfect. Sorry, I'll just get my screen up now. Sorry, that was good. Here we are. Perfect. So good afternoon, everyone. Thank you very much for the opportunity to come and talk to you today at Data Science Oxford. So during my presentation, I'm going to be looking at the impact that COVID-19 has had on the recruitment industry and what the future may look like. So firstly, my name is Dan. I'm a sourcing consultant at Corriculo, and I've been with the company now for around 2 years. And during my role, I'm focused on sourcing candidates and utilising LinkedIn to find top talent as well. So in terms of Corriculo, we're an IT recruitment agency with our offices based on the Oxford Science Park. And during this period, we've been trying to help as many candidates out as possible. A little bit about me outside of work. I enjoy playing cricket, and I've recently started taking up French on Duolingo. So I'll get started with a little bit about sort of the recruitment markets and what we've seen recently. So during the beginning of the year, we saw quite a strong market with an increase in job opportunities in January of around 25%. This was also seen within the contract market, as well as a steady market despite upcoming impacts of IR35. We also saw on the client's perspective several difficulties in attracting top technical talent to the team, which was leading to long times to fill roles. And one thing we saw was clients were looking to increase flexibility and remote working options that they're providing to candidates. Then, as the lockdown occurred, we saw governments advising companies to work from home where possible and avoiding avoiding large groups and steering clear of pubs, restaurants, and gyms, which I've managed to do throughout my life so far, avoiding gyms. And we also saw several companies continuing to actively recruit, with obvious changes happening with virtual interviewing and onboarding. During this period, we also saw the sudden U-turn on IR35, with the plans delayed until the following April, which is likely to come into place in April 2021. Before this time, we saw a lot of contractors exploring permanent opportunities, and this is a theme that we're expecting to see throughout the next year as well. From this period of candidate side of things, we saw a big impact on the job market, with a huge pause in the number of live and new roles coming in, with around 95% of new positions across both permanent and contracts being falling. So this was also mirrored across in the US. One thing we did highlight is that this wasn't very similar to what we saw in 2008 and 2009, with the last recession showed very much a gradual slowdown in the job market, whereas following COVID-19, it was very much a halt in the job market in the space of just a couple of days. Then the impact that this had on the client side of things, obviously companies had to place large numbers of staff on furlough, which also led to companies having to delay start dates, as well as in extreme cases having to withdraw offers for candidates despite their status or potential position within their job search as well. We did see some clear differences occurring within the different sectors. So obviously healthcare and e-commerce continued to remain recruiting during this period, while other industries such as leisure, travel, and the financial services all were majorly affected in the other direction. During this period as well, we did see companies continuing to remain set on hiring candidates, with hiring managers moving towards meeting candidates virtually. A recent report that we ran found around 64% of clients were willing to interview and then offer candidates virtually, whereas up to 9% of candidates were open to accepting a position having only virtually spoken to the team as well. Also, this led to companies having to completely rejig their hiring process and the onboarding. One thing, speaking to a couple of candidates recently, I had a candidate who started a position with a local company, and he was telling me about how they were utilizing the Zoom breakout rooms for him to meet the development team. So they said there was very much like a speed dating exercise where he got to meet each of the different members of the team and get to talk to them for about a minute. So that was quite an interesting thing that he mentioned to me as well. There's also been a few reports out via LinkedIn about the overall UK job market, which we've seen on average is down by around nearly 40% across all sectors, with software and IT tracking above the national averages there as well. Then, as we moved in towards May and June time, we saw a large increase in the number of candidates appearing to look for new positions. This occurred due to several different reasons. Firstly, sort of a direct risk and sort of occurrence of redundancy and furlough, with a direct loss of impact influencing a large number of candidates coming onto the market as well. There's also a large concern within individuals from technical roles that the risk of sort of potential sort of downfall in jobs may have sort of on their long-term sort of career progression. So we were seeing individuals worrying about sort of the risk of spending a prolonged period of time on furlough without having sort of staying up to date with local new technologies. Hence, they were working on personal projects and doing other things to sort of remain active in their work. We also saw a couple of candidates highlighting the treatment of their employer during this period as being a potential reason why they're being pushed away from positions, with some candidates highlighting the fact that there was a lack of communication or the movement to remote working didn't quite occur smoothly within the job market. With in some cases, we also saw that companies were encouraging people to come into the office whilst going against some government guidelines to work from home where possible. Otherwise, we did see companies managing to still attract sort of talent to their organizations by being able to offer sort of genuine opportunity and a new challenge for people to join their companies, despite the sort of apparent risk of changing positions during a global pandemic. Also, companies had to quite extensively adjust their onboarding process to help with initiating sort of candidates from working from home environments. Then a reminder on sort of where we are in 2020. So this is very much an unprecedented period of time where we haven't really seen anything like this before, and the real wider impact of the pandemic will become clear after we see the removal of the furlough scheme, as it's currently acting as a plaster over potentially a deeper cut, which we're yet to see the true impact of. So one thing to note about sort of Oxford as a location, we're relatively lucky to be home to a number of startup organisations who are relatively well funded by both the university and privately. So we're likely to see the increase in those during this period and following a potential recession period as well. Also, several sectors are likely to see increases in funding, with healthcare and research and development also expected to see increases in the future. We've also noticed now being quite a good time for companies, if they do have the capacity and funding to grow their technical teams, with the supply of technical staff being loose from now, compared to any point until around 2013. What we're doing is we're also monitoring our wider client base and contacts to find out sort of about the supply of new positions, as our research sort of suggests that Oxford is around sort of 90% lower in terms of the new roles that we're working compared to last year, although our recent survey shows that from May, around 10% of clients are likely to increase their recruitment over the next 3-month period as well. We're also releasing regular data as well related to the number of candidates looking for new roles, which is widely available on our website and LinkedIn platforms as well. Fortunately, sort of related to data science now, data science has sort of remained a buoyant industry within the UK, with a study in 2019 suggesting that around 80% of companies are either currently or planning to hire a data scientist over the next in their organisation, as well as yearly salaries for data science continuing to grow healthily in both the South and Midlands area, with slight differences occurring sort of geographically in the UK as well. And despite the reduction in the number of jobs advertised for data science, we have seen an increase in their market share, which I believe increased to around 2.6% of all positions advertised. So that's a sort of good sign for the industry that we're working in at the moment. And then finally, what are Corriculo doing to help during this period of time? So we offer quite a unique service, which is called a Corriculo approach. where traditionally what we do is you have a cup of coffee with candidates and get to know them and their individual situation, and then be able to provide them with sort of future career advice and looking to give them tips for interviews, how to adjust their CV accordingly. And if anyone is interested or knows anyone that would be interested in one of those sort of approaches, obviously now we've been getting used to doing them over the phone rather than at Northern Centre on the Science Park. Feel free to get in touch with us about that. And from a client's perspective, we've been carrying out market sentiment analysis recently, as well as providing a range of market intel and guidance for clients who may be tempted to look into adding to their teams at the moment. And we've also created a redundancy advice pack for staff that have been sort of unfortunate to be let go, which we're more than happy to share with individuals if that's something that would be of interest to them as well. And one scheme that we've recently introduced is the Corriculo Marketplace, which is a heavily sort of discounted short-term resource, which looks to pair local companies where you've got potentially an upcoming project where you need an extra pair of hands for start companies where you potentially may have sort of someone not quite having as much work to do, and this sort of acts as a sort of place where you can sort of organise the exchange of staff, and we've had a couple of successful cases of this happening now. So thank you very much for your time today, and if anyone has any questions, I'll do my best to try and answer those for you. Thank you.
Thank you very much, Dan. Really appreciate Corriculo, perhaps one of the premier recruitment companies in the Oxfordshire, Thames Valley area. Certainly, from what you've told us, the most caring of our community. So thank you very much for that. Okay, so without any further delay, let's move on to John McLoone, who will be talking to us about big data. Thank you very much.
Thank you. And perhaps by way of segue, I should say to Dan that we are hiring. So if you wanted to get in touch, maybe you can help us out. So for those of you who don't know Wolfram, we are involved in all kinds of computation, been around for about 30 years. Most people know us through the Wolfram Language or the Mathematica application, but also we serve knowledge queries to Siri, Office 360, and the Amazon equivalent, which I can't mention because she's listening. Now, what I do is I lead the technical services team in Europe here in Oxfordshire, and we do mostly data science projects, but other kinds of computation projects for customers. And as was mentioned, we've got some technical talks coming up talking about how we do things like build neural networks. But today, I wanted to give a very non-technical presentation, really walking through some of the discussions that I have with the managers that I deal with who are non-technical but need to understand how to handle AI type projects. And I wanted to go through a bunch of issues that are essentially a summary of the conversations that I end up seeming to have over and over again with those people. So let me share my screen here. And basically that I'm going to run through quickly how I sort of talk to them about what AI is and what it's for, issues to do with bias and data quality, validation, and how you actually use this technology practically to make decisions, and then these sort of background issues that come up a lot of ethics. So I start by trying to, I tend to do the opposite of a lot of people in my industry, and I try and de-hype AI for these people because there's a lot of bold claims being made for it. But I start by trying to explain to these purchasers that AI is actually, in a way, nothing special. It's nothing that we haven't been doing for years. It's just got better at it. And I try to explain it purely as being a model with predictive power. And I always bring them back to the simplest thing that they would have done at their own GCSEs, where I say, let's say we measured distance over time for a bunch of journeys, and we want to make some kind of predictions. And that's all AI is doing. I point out to them that we come up with some model, like the straight line model, a plus bx. We tune the parameters of that so that it somehow captures the essence of the model, and now we can start making predictions. We make a best guess of, at this time, where would we be, and we can start filling in gaps, and to some extent we can extrapolate. And all neural networks is, and all of the other machine learning techniques that get labeled as AI really are just this, but for more efficient handling of bigger data and techniques that handle multiple dimension inputs very well. So however much it seems like magic, and perhaps it's like Arthur C. Clarke's third law, that any sufficiently complex model is indistinguishable from intelligence, in the end, it is still always just a model running some numbers and making some prediction that we suppose will tell us something about what will happen in the real world or what has happened. So then I run through that, you know, one of the first barriers I find is that broadening the mind for what these sort of tasks like classification and prediction can do is a real leap of imagination, because certain kinds of classification seem to be very easy to get your head around. So I tend to show them things like text classification, and I do things like I love talking about maths and having that categorized in various ways, but show them that the task of putting some data into a class, whether that class is what language is this thing, or is this a positive sentiment or a negative one, is exactly the same thing regardless of the data. So getting them to see that as the data changes, and I've been raiding my fridge ready for this, so here's a prediction of that image, a Brassica italica, or you see the kinds of things we have around here, edible bananas. That's just another classification task. And likewise, when we get into predictions of how much money will I make, or what's the price of this flat, realizing that predictions come up a lot, where anything where you're filling in continuums, like the color space of a black and white image, is just another form of prediction. So I try and get them through a range of very different examples to start getting a feel for, okay, you've got a blob of data. What are the things that we're trying to predict? Is it what comes next? Is it some value? Is it a class? What are the classes you care about? And so on. But the first hard lesson that usually they have to learn is that that it's not magic. That I give them this definition that machine learning is for when you're data rich and understanding poor. And there's of course a flip side to that, that if you're understanding rich and data poor, there are better techniques out there, sort of classical modeling techniques, or just using the humans that you're using to make decisions now. And we end up early on in discussions about how data rich are you? People think they have data, but very often it's poorly labeled, if ruling out supervised learning, or it's just simply poorly captured. And one person's big data is another person's tiny. That you know, I've dealt with people who are handling data that is big by mind standards, beyond our realm, where things like our customers at CERN are capturing terabytes a second of data. That's truly big, but you have other people who say, I've got this big data problem. What they mean is, I've got more than I can remember in my head. And you end up with a spreadsheet with 100 rows that you're never going to do any decent machine learning from. So some of these projects start with a conversation about how they can capture the right data, and then come back and talk to us in a year when they're starting to accumulate useful data that can actually be modeled. Or it's about how to take their messy data and turn it into something that we could do something with. But half of the conversations I have die at this step of, so show me your data. So then the next thing that usually comes up for managers is they've all heard issues to do with bias. And this is a slightly more nuanced and tangled conversation about trying to avoid biased predictions. Because the first lesson I try and give them is that bias isn't bad. In fact, you want bias. The whole point about having a model is to discriminate. That if we have some data that allows us to decide to hire a person or not hire a person, or to buy a share or not buy a share, we want that discrimination. We want it to decide between different cases and not give us a, oh, everything's nice, it's all equal kind of answer. So it's important to understand that the bias that people worry about actually is what I prefer to label as prejudice, which is unjustified confidence in the data and the quality of predictions, is what it all kind of amounts to, which falls into classes of just insufficient data to make predictions. So, you know, a classic bias might be, I met somebody from Oxford who was horrible, therefore I don't like people from Oxford. one data point is not enough to infer anything useful, and you have to be careful if your data is small that you are simply encoding random predictions just because that happens to be the sampling that you have. And then you have the bad data itself, either because it's been collected badly or it's just wrong. It's just false data that you've been fed. You know, I have been told that people from Oxford are bad people, and I haven't even got data to verify that, but somehow I've encoded that into my decision making. So we then start to break that down. The first is the easy one. Everyone seems to get the idea of false information. It's worth going through the sources of the false information. Of, you know, is it unreliable sources are an easy one to get your head around, but people also tend not to think about their processing and collection techniques. And this is where a lot of the kind of worst systematic false information gets injected, either because the way that you sample people for surveys, for example, is unbalanced, and you're only talking to a subset that doesn't represent your target, or much more subtle things in the processing. You know, a classic one is aggregating data, that you capture people's salaries, and then you go and ruin it by putting them in bins of 0 to 10,000, 10,000 to 20,000, 20,000 to 30,000. And your choice of those bins, these kinds of little processing steps that you think are simplifying the data, they're the things that are injecting a signal that was never there in the first place. And generate these weird boundaries between that 20,999 and the 30,001 value, and things like removing outliers, that people know they have to clean data because there's junk in the data, but the process of removing the junk actually sometimes strips out the interesting cases. They're not outliers, they're actually evidence of a signal, and by removing them as, oh, that must be wrong, or those are unusual cases, then you're actually stripping away some of that signal that is exactly what you would like an automated system that's got the sensitivity to make a model out of those seeming outliers and realize what the pattern is. That gets destroyed by data cleaning very often. One people tend not to think about, though, is various kinds of hostile data. And I try and get people to think about that there is interactivity between the data, where it comes from, and how you use it. It's not, these things are not set in stone as facts. So the first thing is, awareness of humans' awareness that data is being captured already changes the behavior. If you want to ask somebody and you get your notepad out and ask them how many units of alcohol do you drink a week, you're going to get a different answer than if you followed them around, not telling them why you're following them around, and noted down your observations. As soon as they know they're being recorded and have some sense of where that data is going to be used, then particularly subjective things start changing, either because you're watching, they start behaving a bit better and drinking less, or because it encourages them to misremember or misrepresent data. And when things are incentivized, that gets even worse. If there is a reason to lie, then people will lie. And I have two examples I always like to cite that have just different kinds of incentives. Let's do them in the opposite order first. This is actually taken from my own personal life. For a while, I was getting a lot of offers from Ocado, and this is one of the vouchers I was sent through the email. And that's because I was a hostile customer from a data science point of view. We ran two accounts. Whenever we wanted to buy something, we used account 1, and the data science indicates that this is a customer who likes to shop and does not need to be incentivized. And account number 2 that only ever shopped when it got promotions. And the whatever data science Ocado were doing picked up on this and realized that account 2 needed to be sent every promo that came around. And so account 2 was flooded with promos, used them when it got them, and anytime we needed regular shopping, we go through account 1. And this is an example of hostile data that is, in my case, very knowingly, but sometimes subconsciously setting out to corrupt the data set by the behavior, because the incentivizations encourage behavior that is not fair random sampling. And then perhaps slightly less practical, but more fun, was the fiasco of the Microsoft Tay chatbot, where the idea was it was a chatbot that would improve its ability to talk to you by learning from the conversations it had, which, if you're conversations are properly randomly sampled natural conversations was a perfectly sensible idea. But of course, as soon as it got onto chat groups, most notably 4chan got hold of it at the time, there was an incentivization, for the humor of it to have conversations with the chatbot that it would learn from. And in the space of 24 hours, it became very sweary and very racist. And that was entirely through active insertion of bad data by people who thought it was amusing to have racist and sweary conversations with the chatbot. And within 24 hours, Microsoft had to shut it down. So you always want to look at what is affecting your data capture, unless it is totally kind of captured randomly and silently from the population. There is always going to be a feedback loop involved. Now, that leads us on to this question of sampling. The key thing, of course, is your training data must be representative of your target data. And I often show a little toy live computation example where I use, I'm using Wolfram Language here to do basic classification on a woefully inadequate data set. So I've captured some supposed heights and the gender of the person that they came from. And we run the computation and it produces a classifier, and I can put a number in and get a prediction out. Now, obviously, anyone in data science knows that 7 data points is not really enough to build machine learning classifier, but it's done its best with the data that it has. And I show them this example where we've got this 1.67 height. And if you look in the data, the only sample that was 1.67 was a woman. And yet it's made this prediction. And the reason why it's made this prediction is that there's always more going on in data sets than you think about. And one thing which now when you look back at it, you can see that without any context in the world, one thing it's going to see from this is actually the world is mostly full of men, because we've sampled very poorly here. We have 6 male sample points and only 1 female. So when you actually look at how the model predicts according to height, you see that the prediction of probability that the person is female falls as the heights go up. So the model has learned something from the data, but actually it's learned so little that it's basically slightly less than 50% chance that it's a woman, regardless of height, because that's the main lesson it learned, was that more than 50% of the data set was male. Now, while this is a good example of why you have to be careful to collect data reasonably, it's also a good illustration, I think, of having always to be very careful of the question you're asking. Because this actually might be a good predictor. If the target environment was, I want to predict the gender of people I meet in the male changing rooms, then in fact this data might be representative of that group, or some very male pastime or job role. So if the data doesn't have to represent all of the possible values that you might sample against, it has to represent the scenario in which you're going to apply the AI. And I always try and get people to think about, it's all very well to get the opinions of all ages and all genders and backgrounds on what they think of your product. But if in the end you're going to be marketing your product at 16-year-old girls, then they're the only opinions that matter in terms of building a predictor. Having representative data is only useful if everyone's going to be represented in your target application. Now, of course, this is the one where it gets also a bit thornier, is humans getting involved. And I always tell people that humans automatically pollute data. There's no really getting away from that. That as soon as humans have a role in defining the truth, and if we're talking about truth, things like the ground truth in supervised learning as a key example, then you're no longer predicting what will happen, you're predicting what people said would happen, which might be a valid thing. If you're trying to predict behavior, you don't care what the reality is, you care what people will think. And then the human truth is the one that you want to capture. But if you think you're capturing reality and you're using any humans involved in that, then they're always going to taint it with their prior experience, particularly any measure that is subjective. If you want to say is something good or bad, or you don't have a sort of quantitative measure of something, and your measure is how, what's the person's height, and your surveyor is looking at them and guessing, then you have human versions of truth creeping in. But I also try and warn people that even when they actually are measuring something very quantitative, they're very often not measuring the thing they think they're measuring. You're nearly always measuring some proxy of the truth that that you're interested in. Now, very often it's a very close proxy, but it isn't necessarily the actual value. And there's a classic example that was controversial at the time that that illustrates this quite nicely. The Pennsylvania Board of Probation tried to make a predictor about whether certain people would reoffend when released from prison. And it was accused of being racist. Now, I don't have any opinion on whether it was a good or bad model and whether it was racist, but it's an interesting exercise to think through this thing about measurements and proxy measurements and human involvement. Because here's the model that conceptually this thing was trying to do. They took past people who were released from prison, and they wanted to know, do they offend or reoffend? And the argument is that these people would make is that this was based on truth. They weren't asking the parole officers, who do you think will reoffend, in which case the AI would be just strictly encoding human bias, but they were looking at what actually happened. But of course, if you actually get past a simpler model, what actually happens is much more complicated. At the point that somebody gets released, they might go down the don't reoffend route, and what they were measuring wasn't reoffend, they were measuring convictions for people released as a proxy measurement for not reoffending. So obviously, nearly everyone who doesn't reoffend doesn't get convicted, so it's fairly accurate down that route. But on the people who do reoffend, some of them get caught and some don't. So the not convicted includes people who reoffended but didn't get caught. Of the people who got caught, some get prosecuted, some don't. Sometimes there isn't enough evidence. Of the ones who get prosecuted, some get convicted and some don't. So all the way down this route, to get to this proxy measurement of convicted, there are all kinds of things going on that actually are muddling up the two proxy measurements. And so the argument goes that whether people get caught might be an influence of the effort police put into pursuing them, and whether they get prosecuted might be down to the attitudes of the prosecution board, and whether they get convicted might be down to the attitudes of the judge or the jury, and all of these steps might be tainted by racist attitudes, and therefore the actual proxy measurement is being tainted by the humans involved in all of these steps. What we really want to measure is these two things, but we don't know that. And we really, in practice, we can't know that. And so all we can do is use proxy measurements. So we always have to be asking ourselves with what are we really predicting? And this is a key point where you have to really inject human intelligence. Are we predicting who will reoffend? Are we predicting who's learned most by going to prison and has learned the tricks of not getting caught? Are we learning who the system will pursue most robustly? Which are the things that we're getting out of this model? And is that actually useful to the thing we're trying to achieve? Or is this something that we need to find some way of compensating for? Another discussion I often have is that biased in the space of biases, inaccurate data isn't actually bad. It can be systematically inaccurate and so utterly biased, but that doesn't mean that we can't use it for prediction. The key thing is that whatever the bias is in your collection has to be equally represented in the data that you used for to apply your model. So again, a good example here would be self-reported alcohol consumption. Generally people, when asked about personal alcohol consumption, under-declare. If somebody's drinking 20 units a week and the doctor asks them, they usually say, oh, I drink about 10, 15. If they drink 30, they say they drink 20 and so on. So it's not true. It's entirely downwardly biased. But if what you want to do is to predict whether somebody is at higher risk of an alcohol-related disease, then it's actually still perfectly valid to ask them to self-report. Because if you've trained a model based on self-reported data, and then you ask the patient to self-report, and put that in, then it's effectively the model will compensate. It knows everyone halves their number, and so the model will still be calibrated against that half number. What you don't want to do is to train it on self-reported data and then actually bang the table and say, no, you've really got to tell me the truth. It only works if you tell me the truth and get an accurate number, because actually the two won't be consistent and you'll end up with an overestimate of the risks. And this goes for sort of all kinds of data collection. Try and keep your methods consistent, and then even these biased data sets can still be very useful. Another hot topic on the management of risk here is the protected and sensitive classes. So we're talking gender, race, and disabilities and so on, where there are legal protections against biases, and there is a real opportunity, both from a legal point of view and perhaps even more importantly from a PR point of view, to make sure that you don't have badly biased AI getting you into trouble against these protected classes. And one thing that I try and make sure people are aware of, and this, to be honest, this is a really tricky topic to deal with, because the first thing to learn is it's not enough to exclude the prohibitive information. That even if you're not asking the question that you're not allowed to ask, if you capture enough data, there are correlations that allow you to actually still correspond to that signal, even though you didn't collect it. And I was actually looking at the data here. This is slightly cherry-picked, the numbers, but the broad truth of this is correct. As an example is the EU ruling on gender and car insurance, that men are generally a higher risk of accidents in driving, and therefore tend to have higher premiums. And in 2012, the EU ruled that it was not permissible to base the offer of car insurance on gender anymore. In the year that that rule was brought in, men were paying on average £27 a year more for car insurance. When they stopped asking what and recording whether people were male and female for car insurance purposes, by 2017, the difference was £101 that men were paying more for their car insurance. And the reason is that actually it's pretty obvious if you're a man, from a car insurance point of view, by things like the kind of cars you drive, the miles you do, the previous accident records, the jobs you do. And so, you know, a scaffolder with a sort of hot rod souped up car doing lots of miles a year, or painted in black, or somebody who's a midwife with a small city car painted in pink. There are correlations here that allow you to know. And it's not that the AI is picking out, we can predict the gender, and we shouldn't, and you can just turn it off. The AI doesn't care about gender. What it cares about is risk. And all of these risk factors are all tied together. The fact that you're a scaffolder with a fast car makes you a higher risk. Now, the fact that the root cause of those might be to do with testosterone and male upbringing doesn't actually matter. But you're left with a real tricky problem of what do you do about that? Because you can stand by the truth of the risk, and then you expose yourself to having to defend that it was genuinely risk factors and not the riskiness of being male that caused it. Or you can adjust for the male factor, but then effectively you're taking a woman who is exactly the same risk profile and having to raise her insurance premium versus the man of the same profile, because in fact, in order to achieve the same risk profile, you're effectively having to subtract out the maleness, and they're actually not really the same risk profile at all. They just have the same background characteristics. And so you're effectively, arguably, injecting an anti-bias by trying to compensate. So it's a tricky thing, but all I try and do is raise awareness that you can't simply not ask the question and think this issue has gone away. And it's more important to worry about the kind of sources of your signal to make sure you're not encoding prior human biases around those protected issues, and that you are at least making sure that you aren't accentuating the issues. The next big topic that I come on to is the basic idea of should we use it, the validation step. And the first hurdle I have to get these people over usually is the principle of validation is nothing to do with why or checking your work. We're all brought up in a school system that says you've got to explain the model. You've got to think through why the model works, and you've got to check it to make sure you haven't made any mistakes, and you've got to take into account all the things that you have to think about as you write the program, and you've got to be able to explain to your manager the steps that it goes through and so on. And people are uncomfortable with the black box. We run this magic process on some data, a predictor comes out, and they say, well, so can you explain it to me? And in the end, you have to embrace the unknown is the key message. And the key question that matters, the only one that really matters, is does it work? Not why, just does it work? So I walk them through the whole principle that what we have to do is test it. If it makes good predictions that will make you money or avoid accidents or whatever the thing is that you're trying to achieve, then we use it. And if it doesn't matter how clever it is, if it's not making useful predictions, we don't use it. But I've certainly seen people fall into the test versus training data set problem. And so I like to show them an example of why we have to separate our data. And because it seems like the more data, the better. We've got all this data, so let's put all of the data into training the best possible model that we can. And then all you're left to test it with is either testing it on data it's already seen, or testing it live against the future without knowing whether it's going to work. So I throw them back into really toy examples, and I do a machine vision classifier for them, and I say, here's an example of a dog labeled as a dog and a cat labeled as a cat, and we're going to do the convolutional neural network classifier to make a predictor, and then we can test it, and look, it works. We give it a picture of a dog, and it says dog, and we give it a picture of a cat, and it says cat. But of course, it's seen those two examples. And in fact, this is all it knows, is that those particular examples. It's inferred nothing useful about the underlying thing to be learned from pictures. And so as soon as I show it any picture outside of that data set, it's essentially random, which it's going to get. And so we talk then, we start having conversations about holding back 20% of the data to make sure we are really testing it against something that it hasn't seen. And it leads us into conversations that are kind of an eye-opener for some people is, and here we are getting into a much more technical space, but I like them to understand this concept of over and underfitting. That arguably, in this case, we've underfitted because we have learned nothing underlying about the essence of our problem. And in our example we had earlier, our simple straight line fitting, here is our essence that we've managed to pick out. So we haven't fallen into that problem of capturing no essence. We can see straight away that it's kind of got that essence. And we can talk about how with better models and more data, we can kind of improve that. We can get a better fit by, saying, well, let's give it more freedom to fit, and maybe the essence of this actually has a bit of a curvature to it. And then I take them through this to the extremes, and I turn up the freedom in this until it starts getting these kind of crazy bumps in it. And I take it to the full extreme. I say, here is a model that, in terms of testing against the seen data, is absolutely perfect. It's not even missing a single point. Every single point we've seen tests perfectly against this. But in terms of predictive power, it's worthless. That as soon as we step away from those points, it massively undershoots and overshoots. And this is how I like to introduce the concept of overfitting, that what we're no longer capturing is the essence or truth of our data set. What we're really capturing here is the random noise, the unmeasurable things that might have been if this was travel times, the random delays and the traffic jams, and it'll never be reproduced, and we aren't capturing it. We can't use it for prediction. We just have a model that tries to fit those random noises, which is of no use at all. So then we then get drawn into conversations about, so how do we measure success? When I say if it works, it's good, and if it doesn't, well, what does works mean? And I'm not going to go, I'll save these kind of examples in more detail for the future technical talks we're doing if you want to return. But I often show them through different kinds of validation, where this is using a great classic, the MNIST character recognizer that takes pictures of characters and guesses what they are, and makes some test data and measure it. And I start them with the introduction to the headline number, that this model is 98% accurate. In 98% of cases, it has correctly classified a 5 as a 5 and so on. But the conversation has to always fairly quickly go into the conversations about what is the nature of failure. That it's not enough to say that we got it wrong 2% of the time. And my first favorite point is to show them the confusion matrix and say, so this is a little bit small here, but the cases of true 9s that were predicted as 9s. And you can see that there are certain cases where true 4, for some reason, is disproportionately coming out as prediction 19. So this is our major error case, is 4s that look like 9s. 9, not 19. And the next worst case is 2s that look like 7s. So then you have to start thinking about, is that a particularly good or bad error to make? And we end up in conversations about, and if I just get out of this here, let's forget numerical predictions here. So we'll come back, sorry, to the nature of decision making, but this kind of nature of failure leads to the way that we make decisions. But before we leave validation, I always try and get them to think about change, because they always come to me with a data set and they want to make something that will make predictions. Classic one is I obviously have conversations with people in hedge funds who want to make money, and they want help making a model that will say, should I buy this share or sell this share? And if we can make a predictor that can predict how the market behaves, then we can make money. And isn't that a lovely dream? But the two things I try and lead them through thinking about is that the world changes. That what might be a good prediction, even in things like stocks and shares last year, well, now we're in a different world than we were last year, and COVID is just one thing that's changed all of that. That the relationships between seasonality in clothing retail has just changed. That when people visit shops between going online, that's just changed now. So this past behavior is not necessarily a predictor to future, but you have to think about what's that interval of change. That if you collect data for a year, you can always be collecting a rolling year. You're going to have a very slow changing algorithm. But if you collect data on every day to make predictions about what will happen tomorrow, you've got really fast changing algorithm that could stay up to date with social trends that can turn on a single tweet and change the way the world behaves for 24 hours. But you don't have much data, so you're not going to build up a very good model. And that challenge of what's our interval of change in the industry that we're in is an important conversation, as is the conversation about how will the world react to what you do. And this is sort of financial trading markets is a sort of classic example of that. If I was an absolute genius at AI and I could build a model that could 100% predict the markets, it would make huge amounts of money for a short amount of time, because it would be predicting what everyone else is doing. As soon as everyone else starts losing money, and every time they're in some bet against us on the markets they lose, they're not going to like whatever their decision-making process is. And they are going to change in opposition to the way that I've perturbed the market. And so as soon as you start outplaying somebody, particularly in a kind of game theory scenario, they are going to change their behavior to try and compensate. And there's a lot of theory about Nash equilibrium about this, that our world is so complicated that you'll likely never settle in that. But whatever it is that you're doing to your opponent using AI will cause them to change their behavior if they can see that influence. So there's this question here about how fast are we going to change, because very often the conversation is, make me something that I can then use. And I always try and turn, after the proof of concept phase, that conversation to how are we going to build continuous evolution of that model into your world. So that's all the kind of the model building, but in the end you have to make decisions. And this in the end is perhaps not such a complicated topic. It's all about there's a cost benefit question of if you have to get the customer early to realize that you are not going to make 100% predictions. This modern AI methods are all probabilistic. A good one will be right more often than it's wrong, but it will be wrong sometimes. So you have to trade off the opportunity of being right and the cost of being wrong, and how much of each you're willing to, how much wrong you're willing to tolerate. But the self-drive cars is a good example of this. That there is that as well as that optimization of, if it's trading, I don't care if I'm only right 51% of the time, because that thin margin is enough to make money. In hospital treatment, 51% of the time for deciding to give somebody some major treatment is not good enough. It's very contextual. But it's also, it can't be taken in pure isolation of cost and benefit. You also have to always ask, is it better than the alternatives? And self-drive cars is a good example of this one, where a lot of the narrative is about, will it kill people? If we let a self-drive car loose on the roads, is it going to kill people? And, I always tell people when I'm asked about that kind of issue, the answer is yes, it's going to kill people. But in terms of the decision about whether or not we put self-drive cars on the road, it doesn't matter. It's not the right question. The right question is, will it kill more people than letting a human drive the car? And while the managers are sat there imagining themselves in front of a journalist or in front of a judge, answering the question, so you put a car onto the road knowing it would kill people, and trying to figure out how to answer that. That's a kind of rhetorical challenge, but the decision making here has to always take into account, am I net improving things by taking humans out of driving the cars? So, if we kill 9,000 people with self-drive cars compared to the 15,000 we kill every year on the road with humans, then we should do it. Broadly speaking, there is a caveat to that, which needs to be thought about. So whenever we're sort of weighing up the better than alternatives, very often that alternative is humans. That things we're trying to automate with AI are generally replacing humans in the loop or augmenting humans. So, humans have weaknesses, and emotion and history is where a lot of this human bias comes from. You remind them of somebody that they knew once, and therefore they're not going to give you a loan, and they don't even know that themselves. And then there are other practical things like humans are slow compared to computers, and humans get tired. And if you need a kind of error-resistant state, then having a human screening thousands and thousands of cancer cell photographs, fatigue becomes a major issue. When you look at the human strengths, actually some of them are exactly the same as the weaknesses. The emotion and history is exactly the kind of thing where AI lacks context, and you're going to have those kind of situations where the rational thing is to say, no, you can't have the loan, or no, you can't have the job, or whatever it is you're trying to predict. But any human would say, actually, if you tell the whole story, this is different. This just doesn't fit the model. It's outside of the experience of the AI. And that adaptability of humans is important. So these are the things to trade off. Are you, getting rid of bad emotion and history and solving all of these deployment issues at the cost of the useful emotion and history and the adaptability? And there's no computable answer to that. This is a kind of a human intelligence thing to decide. And this sort of balance of outcomes is that I kind of alluded to with medical diagnosis is a sort of key example of what you even then do with that model when you get it. It's not enough to reduce things down to probabilities in that kind of very machine sense. It's still often, it's a human decision what to do with the prediction. And so there's, again, toy example I like to show is this sort of toy data set of some diagnostic measure that returns some number, and when it's low it appears to say you're healthy, and when it's higher it appears to say diseased. And we can make some prediction from that, and we can say what's the probability, well, let's say what's the diagnosis for the number 2.5, and the answer is healthy, don't do anything about it. And we can drill into that and say, according to this model, actually it's pretty borderline, it's a smidgen above 50% prediction that it's healthy. But that's only a probability. Our decision has to take into account all of the consequences. And you can imagine some extreme scenarios where well, you've got a bit of a headache, give the person aspirin anyway. If it might help, why not? It's a cheap drug, it has no side effects. If you think it might help, even if the probabilities are against that, why not? Unless it's kind of like 99% waste of time, then you might as well go with treatment. So the threshold for making that decision would be really low on the diseased. You take something like maybe cancer diagnosis or some kind of heart intervention where chemotherapy is a really serious step to take. Putting somebody through chemotherapy on a 0.0027 margin that it would do them some good is not a good decision to go ahead. Now, this might be a high enough probability to say we need further investigation and we're going to do some other diagnostics. And maybe, again, the threshold for that might be very low. Maybe 5% risk of cancer is enough to say, I think we need to look further. But you might need more like 75, 80, 90% chance that it's cancer before we want to sanction chemotherapy. So that's where, again, human intervention, either just subjectively or encoded in some way like a cost function that allows us to say 1 point for getting it right if you're there healthy, but there's a penalty point for saying healthy if they're actually diseased. We want to punish missing diseases, now pushes that probability diagnosis from the healthy zone to the disease zone. Now, another one that is people seem to struggle with, even though it seems to me like a kind of obvious thing, is correls and correlation, which comes up particularly in the application in, are we using AI for prediction or are we using it to control things? And that actually translates into cause and correlation. That, am I trying to change human behavior by changing, or the behavior of some system by setting some values because I know what the predicted effect of that will be, or am I simply trying to predict what will happen next? And so the cause correlation thing is there's some observation and some other observation. So when we see state A, state B seems to happen. And the natural human explanation is to tell stories and say A causes B. But there's other explanations. In fact, there's a dozen explanations, but the three main ones are either A causes B, or perhaps B causes A, or perhaps they're actually unrelated and there's some third thing that causes A and B to happen. And this really matters whether, if we think changing A will change B. With explanation 1, changing A will change B. With explanation 2 and 3, whatever we do to A, it'll have no effect on B. And the one I like to give them is, I can observe, and it is statistically significant, that if we ask whether somebody has a beard or not, we can predict whether they're more likely to crash a car. Therefore, in the control world, we should shave people, because if we shave people, they will have fewer car crashes. But of course, the real causality of this is that it's back to the fact that men generally are more likely to have vehicle crashes than women, and men are more likely to have beards than women, and that's why we see the correlation. And that's why shaving people is not going to prove anything, because it is not a causal variable, and therefore we cannot use it for controlling anything. We could potentially control this by refusing to insure men, but we can't control it through the actual thing that we observed. So of course, then that gets back into our world of decision making and data collection. So the first thing is, if we want to make a predictor that we're going to use for control, we have to use controlled data in our training data sets. We can't just sample from the world. So if we want to, in my beard example, we can sample from the world and measure whether beards are correlated to car crashes. If we want to use it for control, we have to control that by taking some sample people with beards and without and shaving some of them and sending them out to drive for a year. If we control that variable, we can now use it for prediction. And I would imagine it has little causal control and therefore little predictive control once we make it a driven variable. But who knows? I've never actually done the experiment. Maybe not having beards, maybe having a beard is a distraction, and actually it has some small effect on your driving ability. But that would come out with sufficient data. But it would only come out if we, and again, it's like I said about our sampling generally, is the data we collect has to be representative of the environment in which we'll use it. If we're going to use it for control, we have to collect it in controlled ways. And it also is important to try and think, what are the causal variables? To use your human intelligence and say, well, maybe the thing that's causing this is gender, or maybe the thing that's causing it is the having enough spare cash to pay for going to the barbers or something. Then we need to collect all of those things that might actually be causal in this. And with enough of that data, the causal variables will then end up being the things that that we start predicting against. And you'll find that the significance of the other variables fades once you're capturing the causal variable itself. So as a general rule, if your models aren't working, you haven't got enough data. And that's not necessarily volume, that can also be you're not collecting data on enough things that might affect the thing you're predicting on. So the last one topic that comes up in my conversations is often sort of explainability and ethical issues. Very often people want to say, how did it make that decision? Now, I've already sort of set out my pitch to them that all we have to ask about AI type models is, does it work? But they don't listen, and they say, I need to explain after the event, why did it make that decision? And I try and explain, I sort of revert to philosophy here, and I say, well, what do you mean? What is explainability? When a human explains something to you, what are you actually asking them to do? And what you're asking them to do is to have some kind of abstraction that that are things that you recognize. You know, why didn't you give this guy a loan? Well, you know, he didn't have much of a job history. That's an abstraction of the human. The human's this big complicated thing. We know all kinds of stuff about humans, but you've abstracted a feature of that human, their job history, that is something that I, as a person you're explaining to, recognize. So I sort of take a sort of random example here of in this case, Stanford dogs, and I do this thing of what's called a feature space plot, which is we're going to study those for the features that seem significant, and we're going to abstract out the two most significant dimensions with dimension reducing. And you can see it does a really good job of clustering these dogs. So here's our sort of black poodles over here, form naturally into a cluster, our light poodles, our Irish wolfhounds, our basset hounds, and our, I don't know what these are, Jack Russells or something. Now we've got two dimensions that are abstractions of something about the dogs. Now, it would be nice to imagine in our human abstraction, what would we do? We'd say, how big are the ears? That's a good abstraction. Basset hounds have big ears. How fluffy is it? Poodles are fluffy. And so maybe we could have two dimensions like that we could cluster. But actually, it doesn't really do a very good job, because those aren't, you know, these aren't fluffy. These are, but have, I guess they do have big ears. So these are all on the big ear dimension. Maybe it's how pointy the ears are. It's really hard to find two things that could allow you to separate the four breeds. So this has come up with some abstraction. It's learned without knowing these words like ears and noses and any of these things. And I say, well, maybe it's zigzaggy fuzziness. You know, maybe if there was a word for zigzaggy fuzziness and we all thought in those terms, this value would be the amount of zigzaggy fuzziness. And we go, oh, yes, I can see it now. But the thing is, it doesn't have the word. So it's invented its own concept, and you could give a word to it. In this case, y. Y-axis is some word. But if we don't know that word, that abstraction is useless to us, because we can't understand what it's telling us. And this is this kind of like asking a French person to explain to us why they chose, you know, why this is a dog when we don't speak French. The abstraction is useless because we don't speak the same language as the machine. So what can we do if we can't understand the abstraction? And really, there's only two choices that we have. One is a kind of sensitivity analysis. And I do this toy example, I often do this as a live coding example, where I take classic training sets, the Titanic passenger list, and I make predictions on what would happen if I traveled on the Titanic. And it makes the prediction for me. Why does it make that prediction that I would die? Well, what did it use here? The model was logistic regression. So we're going to end up with some curves. So we could say, well, we're here on the curve, but what does the curve really mean in 3 dimensions? It's kind of hard to say, but that's not the worst for explainability. But what we can usefully do is we can say, well, which of these variables explain most the outcome? So I can make a little function here that says I'm going to compare the prediction it made for me, the probability that it came up with that I would die, to a different passenger. And then I can perturb the different variables. I can say, well, if I traveled in second class rather than first, it would shift my probability by 18%. If I stayed in first class, but I was 4 years younger, well, that shifts my probability by 2%, and 5 years older by 4%, and if I was a woman instead of a man, by 53%. So we can now say that that the bigger influence on my personal prediction was my gender, that the women and children first was obviously a big factor on the Titanic. And then the second thing, most biggest influence, was the fact that I was traveling in first class, that traveling in second, or if I went to, let's do this again in third class, that would have an even bigger effect. So it seems like my age had no great influence. But, and here's the but that I always try and make people aware of, that doesn't mean, you can't sweepingly say that gender is the biggest influence on the survival of the Titanic. It is the biggest influence around the reference point that is me. So for me, in this area of first class 49-ish male-ish people, around there is the biggest influence. But if we did the same analysis at somebody who was a 7-year-old, you might find actually the age was the biggest influence, or the class was the biggest influence, or so you can't make these sweeping statements. All you can do is sensitivity analysis around particular decisions, and it makes it something that is a very dynamic question. But the other lesson I try and give them, and back to our sort of collection of data that I said at the beginning that is usually in a shocking state when I start, is the best thing you can do is to explain after the event is auditability and reproducibility. Because you know, if you're capturing everything along the process, capture it, write down how you collected your data. You know, hang on to those forms that you used to capture the data so you can examine what the wording was. Hang on to the training data that you used to build the model and how you partitioned it from your test data. Hang on to any of those sort of tweaks and initial conditions. Hang on to the model. Hang on to the validation data you tested it against and the validation results. Then at least you can go back and say, here's how come we ended up with the model that makes these decisions. And you can start testing well, what happens if we'd used different training data? Was that unfortunate the way we sampled it? Would that have made a difference? You know, you can learn lessons if you keep stuff, but there's a lot to keep there because everything down the process affects it. But then I also always come back to this question of better than humans, because when they're worrying about explainability, I like to point out to them that they think that they're in an environment of explainability now because they can go to Bob and say, why did you give a loan to that person, or why not? But we will have to always ask that question, is it better than humans, or at least not worse than humans in this case? Because human explainability is actually not nearly as good as we imagine it to be. That people make decisions without knowing why. They have a gut feeling that it was the right thing, and it's something to do with their experience. And it might be, you know, really solid experience that they've seen this kind of scenario 50 times before, and in 49 times it turned out this way. Or it might be in that kind of, they have a bad feeling about it because, you know, as I say, this person reminded them of somebody they hated at school, and they don't put their finger on why that was, but it makes them feel negative about the way the person's demeanor was, and they judge them to be an unreliable person and end up making a decision. And even if they do know why, they're not always honest about it. You ask them, so why did you make this decision? Well, maybe their decision was because they were really busy and they just flipped a coin. They're not going to tell you that they were too busy and they guessed. They're going to come up with some excuse. Or if they had some irrational, racist, biased reason, they're not going to admit that. They're going to come up with some excuse. And so humans, whether they know it or not, are not always good at explaining the decisions that they made, any more than our lack of insight into this sort of black box of the AI. But at least the AI has reproducibility. You can put the same numbers in again and it should produce the same results, and then that allows you to test whether or not some particular data point in the input was given unreasonable. You know, the model decided that, you know, the number of cars you owned was the most critical feature at this design point for whether or not you should get cancer treatments. And at least you can find that out afterwards, which you can't with humans. The only ethical issues I touch on usually are to do with privacy, that on the whole, with the exception of nearest neighbor method, which one has to worry about a bit more, the models don't contain individual data because there are a lot of issues to do with privacy, unless you get into the overfitting. But that's for us as the data science to worry about, that an overfitted model with insufficient data can end up predicting data that wasn't in the model. You know, if you have a really overfitted model that you want to predict where in the world you get certain clusters of patients, you know, do we get more COVID in the Northeast? Well, if that's highly overfitted, you could feed it all of the private medical data of some celebrity that you don't know who it is because it's subject to some newspaper order, and it could predict their exact postcode. And you could look up and go, oh, it's that celebrity lives in that house. You might not actually be holding the celebrity's name, but a totally overfitted model can allow us to narrow down predictions that might be representative of only small numbers of people. So as long as we avoid overfitting and the nearest neighbor method, we strip through kind of anonymization on data, then privacy is usually pretty easy to avoid, as long as our data sets are decent sized. There is a legal thing just to consider, though, that GDPR does require informed permission on the use of data. And I always encourage people to make sure their GDPR statements are fairly vague about learning general insights to improve the business model, because you don't know in future what great model you could build on customer data you're collecting. And in the kind of the spirit of GDPR, doing aggregated things that predict how you can make a better product or how your marketing will be received is certainly not breaching the spirit of GDPR. It can technically breach the letter of the GDPR laws if you haven't got at your data capture permissions that you can use it in an aggregated sense for doing modeling. So make sure you get that in early so you're not poisoning your data set against legal repercussions later. But for me, the ethical issues are about understanding human versus computer role, because we don't abdicate our responsibility. It's still human intelligence that makes sure you get good, unbiased data that has been collected nicely and in a representative way, and you've understood the bias, and you've understood, is it causal or just predictive, and how you're going to use that when you make a decision, rather just blindly having it say, if your default rate is predicted to be above some number, just apply that. Think about those criteria. And we leave the computer to make predictions that in theory can be much better in terms of really using that data. And we use the computer to apply those rules so that it can be efficient and accurate about the rules once we've decided the kind of business rules for the application. And it's still a human's job to see, does it work? To measure that in a way that is contextual, that thinks about the PR repercussions of what happens when it goes wrong. And even if it's defensible in a mathematical sense, it may not be defensible in a real application sense, and to worry about those cases. And then behind that is a great deal of data science that we try and relieve the customer of worrying about when we're doing projects, or we sell them Wolfram Language and let them worry about, but that's for the data scientists, not for the managers. So I hope that's given a bit of an insight into the world I work in, and some of the sensible and sometimes rather dumb conversations I have. I wanted to remind you of these much more technical conversations about how we do our data science that we're running, I think, not through the Data Science Oxford group, but they're free to come and sign up. So just follow the links to register. And I hope I didn't overrun too much, and we have some time to maybe answer some questions or on or off the topic I've been talking about. And thank you very much for listening so patiently.
John, that was an incredibly interesting talk, and I work at an economics consulting and forecasting company, and I made a comment on the chat saying that now I understand really quite clearly why our econometricians and analysts spend an awful lot of time poring over their data and doing lots of sensitivity analysis, as you pointed out. But I learned from your talk there are definitely some areas where I think that I could recommend some improvements in my organization. So I'm really pleased that that value has been extracted straight away. And I can also see where things can go wrong. So that's also something I can look out for. So really appreciate that learning that I got from your talk.
Great. Just sorry, I was not concentrating on the comments. So I see comment about should the rich model for don't reoffend include a wrongful arrest path, which of course, yes, it should. That there are people who don't reoffend that do go to prison or end up reconvicted for things that they didn't do. So that should, I'll update the diagram actually. That does make it seem like all the mistakes are on one side of the path. So I'm just reading the other comments here. Oh yes, yeah. Unfortunately, my Ocado trick doesn't seem to work. They have adjusted now, so maybe I need to start a fresh second account, because my second account finally they learned that it was only buying on offers and they weren't enticing it to become a regular customer.
Oh, that's a real pity.
I should start the experiment again. Are there any other questions?
I don't know, but certainly I think my appetite's been whet to come and attend some of your other talks, and really like the way it was presented directly in your tool, which was great.
If anyone do have questions, feel free to mail me directly. So that's my email address I just added to the final slide there. Great.
So what's the tool that you were using, the product that Wolfram produced?
Yeah, so this is our technology that, and my team basically works exclusively in our technology. We have all the expertise in that. So this is a Mathematica notebook that you're seeing here, and the little snippets of code that you saw for the toy examples are Wolfram Language, which is broadly all kinds of computation, but it does include a whole bunch of classification and sequence predicting and a framework for kind of rapid development of neural networks.
Excellent.
As well as classical image processing and all kinds of other data science.
Great. Can you tell us a little bit about your operation in Oxford?
Yeah, sure. So Wolfram is principally a US company. We're about 700 or 800 people, but the majority of those are in Champaign, Illinois, somewhere sort of south of Chicago. And the core of our business is this technology stack that we build. So we license that to all kinds of people for production or just exploratory use. Our Oxford setup is much smaller. We're about 30 or 40 people, and we are the kind of sales and marketing HQ for Europe. So we support our partners throughout Europe, and we also have a sales team that deal with UK, France, and Spain directly out of our office. And then I run a technical group that's in that office that does European consulting projects. So we have teams elsewhere for the rest of the world, but I do projects in Europe, mostly, as I say, data science or kind of interface building deployment type projects. And I also support the sales and marketing team. So we do evangelism type things, giving talks and talking to customers about how the technology can help them. And we also actually have a little side project, which is the computer-based math project. If you look at computerbasedmath.org, that is a project to rethink what a kind of alternative maths education would look like if you assume computers exist. Mm-hmm. So rather than learning how to factor a polynomial, which I can do polynomial arithmetic on a computer better than any human will ever learn to do, and you never use factoring polynomials in real life. You do things like Fourier transforms and things like you never learn at school. So we're trying to come up with an educational pathway that would assume there's computer arithmetic and learns new concepts and ideas like machine learning instead of hand calculating techniques. And so my team also supports that in building out our interactive courseware and the philosophy of that as that's our evening project alongside the day project of crunching numbers for people.
Yeah, I took a look at that briefly, and I thought it was very interesting and something I'll definitely go back and revisit.
And in fact, topically this week, there is my boss, Conrad Wolfram, has just released a book that that spells out the entire philosophy. Here we go, the Maths Fix. It's actually unfortunately out of stock already on Amazon, but there's some fresh prints coming. That is the whole kind of maths philosophy, which I don't think I contributed too much in the actual words, but a lot of philosophy in there came from work I've done with Conrad.
Yeah, marvelous. Can you tell us also a little bit about Wolfram Alpha? Because a few years ago there was quite a bit of buzz about it, but I haven't really heard much about it recently.
Yeah, so for those of you who don't know, the idea of Wolfram Alpha is it's a natural language layer on computation. So anything that's kind of driven by public type computation data sets, I can say, what's the GDP of the Netherlands as a fraction of, or let's do the sales of Philips as a fraction of the GDP of Netherlands. So these sort of flyby queries that require dipping into multiple silos of data. I didn't hit return. Let me try again. So hopefully it'll turn that into some computation that says it's 2% of the GDP of Netherlands. But we've had to pull together from lots of different data sets. I don't know, flights over New York might be a completely different kind of query I could type. So it's not doing search like Google, it's all driven by data and computed. So this is a public website where you can go and play for free on these kind of public data sets. And people cheat with their maths homework or look up, how much fat in a Big Mac the size of Mars and these kind of crazy queries. But we also take that technology and we put it into private data sets. So the idea is that you could plumb this into a database in a company, put it behind the firewall, and the queries would be things like, how much have we paid out in obesity-related diseases this month, if you're a medical company, or which salespeople have exceeded target in France this week, and those kind of queries that reach into the data set and need computing. So that's another thing that isn't actually my team. This is our US team does these projects where we teach it the business rules and the data sets and the language that allows a CEO to do the kinds of queries that at the moment have to get routed to a database team to go and write a report and come back a week later. They can just in real time ask questions of their corporate data. And it's actually this that we use behind things like Siri and Alexa and Office 360. So if you ask this kind of a query, well, maybe not that one, which probably tapped into flight data, but a lot of these knowledge queries get routed to us to be answered from the Wolfram Alpha servers.
Right. I didn't know that this is powering things like Siri and Alexa.
Yeah, and it's just been added to the latest version of Office 360. So in the online spreadsheet, if you type in like a nutrition query like fat in, I don't know, well, let's say fat in a Big Mac, then those kind of nutritional breakdown things can be fed straight into a spreadsheet. So you can type a recipe now in a spreadsheet and it'll make you a nutritional label directly in the spreadsheet, that kind of thing. It's all fed by us.
Yeah, that's pretty awesome. And was I correct in understanding that organizations can actually take the Wolfram Alpha engine and put it onto their own databases and data sources?
Well, take's not quite the right word. With the Wolfram language, you can just license it to us and you can do whatever you want. The Wolfram Alpha stack is sufficiently complicated that you really need to engage our technical services team to do it for you. In theory, we can train you up as we do the initial implementation and hand it over, but I think every customer we have, we continue to maintain that for them because there's a lot of knowledge on ontology building that is kind of too much for customers to take on for themselves. Whereas typing a bit of Wolfram language code, you can learn this in an hour. You can be productive in this and doing data science.
Terrific. The last time we had a Wolfram over speaking to us in the Data Science Oxford group, which was about probably 4 years ago or something. And at that point, there was an opportunity for our members to download some trial software and stuff like that. Do you still have those kinds of initiatives going on?
Yes, we do. You can, in fact, there was a developer version of the raw language without the user interface that you can have for free during development purposes without a time limit on it. And we also do trial versions of the full interface and exploratory environment. And if you need longer than whatever the standard 2 or 3 weeks, whatever, you can help yourself to on the website. Just send our people email and we can set that up. And also things like our deployment environment. We have a mechanism for deploying things so that they can serve web pages, and we could even set that up for you.
Well, that's fantastic. I'm afraid we do need to draw the session to a close, but I do want to say really pleased that so many people turned up for this session with John and Wolfram. Really appreciate that. And once again, I'd like to show appreciation to Corriculo for supporting Data Science Oxford. Please, everyone, do give us your feedback and suggestions for what this group should be presenting going forward. It is your community, and we will definitely rely on you to keep it going. So once again,
thank you for inviting me to take part.
Yeah, really appreciate that. Thank you.
Thanks.
Bye.
Bye.